өдөр хэмэл оюун ухаан дэлхийг хурдтай өөрчилж байна. Гэвч энэ технологи өөрөө асар их хүчин хүч шаарддаг. Тэгвэл AI бидний ирээдүйд туслах уу? Эсвэл ачаалал болох уу? Хэмэл оюун ухаан болон машинд суралцах шийдвэр гаргах чадвар олгодог технологи. Өнөөдөр бид хэмэл оюун ухааныг утас, машин, эмнэлэг ашиглаж байна. Энэ бидний амьдралыг илүү хэлбэр болгож байгаагийн нэг жишээ. Массачусетсийн Амхерстийн их сургуулийн судлаачид шинэ өгүүлэлтэд хэд хэдэн нийтлэг том хэмэл оюун ухааны загваруудыг сургахын тулд амьдралын мөчлөгийн үнэлгээ хийсэн байдаг. Тэд энэ үйл явц нь 626,000 фунтаас илүү нөөц төрөгчийн давхар эслийн эквивалент ялгаруулдаг болохыг тогтоожээ. Энэ нь Америкийн дундаж автомашины амьдралынхаа туршид ялгаруулдаг ялгаралтаас бараг 5 дахин их юм аа.
Specifically, what we're looking at is today what the environmental impact of an AI query is, and also what the improvement over the last year has been.
We've had, a 20 to even more year history of publishing data in this space, showing what our power usage effectiveness ratio is for data centers. We want to drive that ratio as close to 1 as possible. People have understandably, concerns about, is this going to be using a lot of energy? Is it hurting the planet in various ways through carbon emissions?
What we see as the most comprehensive approach to measuring the energy consumption for AI across the full stack. So it's not just looking at the models, it's not just looking at the hardware, it's also looking at the infrastructure and how everything gets orchestrated.
There have been other efforts that look at the inference cost of various AI models. In some cases, the methodology that was used there is not really that close to what a production serving system uses, so the numbers usually end up being much higher because they don't incorporate things like, say, speculative decoding or large batching of requests into making the overall system much more efficient. People were wondering, if I do a Gemini query, is that equivalent to driving a car 1,000 miles? And the answer is absolutely not. The data we gathered shows carbon emissions are actually quite small.
The energy consumption and carbon emissions and water consumption were actually a lot lower than what we've been seeing in some of the public estimates.
Rob, thanks for showing me around. We're going to have a look at the robot that you're using to pave some of the streets in Amsterdam.
Ja.
Would you show me?
Ja, graag. Kom verder. Wat je hier ziet is de stenen die worden aangeleverd vanuit projecten Amsterdam. Die worden losgestort in allerlei bunkers. En die komen dan uiteindelijk worden ze hier in de robot gegooid. En deze mensen die hier staan, het eerste wat zij doen is een visuele controle van de stenen. Dus is de steen beschadigd? Is hij te groot? Is hij een andere kleur? Is het een andere soort? Die filteren hun hier al meteen uit. Alle foute stenen gooien we apart en die gaan dan uiteindelijk naar afval. They make new stones of it. They crush it and there is an ingredient for a new product. En op het moment dat hij goed is, gaat hij hier door.
So these ones are reused, and if you can't reuse it, then it's recycled.
Ja.
We did a life cycle assessment, and we are basically asking the question, how much CO2 is emitted for 1 square meter of bricks to be produced? And to summarize the main results, whatever we have in the road right now is already basically emissions that were emitted, and that is already there, right? That's what we want to use.
And we have developed one clamp for it, so we can lay all bricks. Not every clamp can lay all bricks. This is so different in size, height, length. So you have to have a special clamp. Dus dit is een vierkante meter. Dus als 1 vierkante meter per keer wordt die teruggelegd in de straat. Dat is ook meteen arbotechnisch waar we naartoe willen. Het niet meer handmatig leggen van stenen. When you do it by hand. 100 tot 200 square meters a day. And with a machine, you can easily double it. Ja, en dan is het op zich heel erg makkelijk. Dus je ontlast de stad er eigenlijk mee.
Waste is human invention. We should reuse to the maximum because we want to have a lower footprint, but also we want to have a more sustainable business model. Raw materials, even the materials that are cheap today, will become expensive in the future. So it doesn't make sense to have good quality of materials, throw them away and not reuse them just because they are used before.
But it's not just bricks that make up the built environment. There are also some much more modern pieces of technology that inevitably end up reaching the end of their working lives.
It turns out that solar panels can have a really significant impact. So I've come to speak to some of the researchers to find out more.
Some of the strategies that we're focusing on here in Amsterdam is partially lifetime extensions. And then one of the more high-end R strategies would be high-quality recycling and repair. We are working on a project called Fair PV with Biosphere Solar, Circularize and research departments at TU Delft. And we're developing a repairable, transparent and sustainable solar panel.
What are we looking at here? What is this exactly? It's obviously a solar panel, but what's special about it?
It's a solar panel that has one big difference, which is that it is not glued together. So solar panels have this lamination, which means that they are just one big piece of material, and you can't separate anything. What we do is we only close it around the edges, which means that what we'll do in a second is open it with a hot knife, and you have all of your components right there. We see potential to actually use the materials for new solar panels, which is quite hard to do because silicon has to be, I think, 99.999999999% pure. So if you've got glue and all these things and it's really hard to disassemble, then you won't reach that purity. Yeah.
Currently, solar panels, they're rather downcycled. The aluminium frame can be removed. The glass can be recycled in a low quality. But also the very critical components, such as the silicon cells and the silver within it, it can only be, or it is only shredded and used as filler material for asphalt or concrete.
So this is the operating table.
You have this adhesive around the outside, and then I can see obviously these silicon photovoltaic wafers.
Yeah.
Is that all there is to it, or is there more to it than that?
So the glue also ensured that it sticks together, right? That everything stays in place. So you see these little dots here? Yeah. This can all be removed once heated a little bit.
So just using a smaller amount of adhesive?
Yeah. We're developing a machine to do this industrially. So this is really just to kind of show the proof of concept. All of these cells are set in strings. And what we would do is we would choose either a part of the strings or take the entire string and replace it with the one we showed in the box.
These cells can then be recycled properly, and new high-functioning cells can be installed again in this solar panel. In this energy transition and circular transition, we are basically transforming a whole city. So a lot of new innovations will be used, and this also poses new challenges that we may not have encountered before. And I think what they're doing here very well is we're looking proactively in what kind of challenges these are and how can we proactively solve them.
Some of the actions we need to take to make a city circular require everyday people to get on board. And that includes tackling food waste.
On average, it's about half a kilo of food waste per day per family.
I went to see one simple technology that is being installed in Amsterdam's newly built flats and could one day be in all our homes.
So what am I looking at here?
What this machine does is it dewaters the ground up food waste that we produce on the platform here upstairs. You have a normal sink, and then next to it you have a smaller sink with the kitchen sink grinder unit. So all the ground up food waste that you can see in the plumbing right here essentially flows down and then it winds up here on the other side in this big machine.
Am I right in thinking that normally food waste, or as a standard, the basic thing you can do with it is just incinerate it, and that produces energy?
Yeah.
But there are potentially other things, smarter things you can do with the waste as well.
So you can imagine we're going to make compost or biogas or products like this. Okay. But we're also aiming for higher applications. So for example, the building blocks of bioplastics.
The water is actually a problem in the whole collection system. We first have to, let's say, remove the water, which all cost energy. And that's the whole research about how to use as less water as possible. And once we use it, how to extract, let's say, the food waste from the water again. And after this project, we also look at how to extract the nutrients that are solved into the water, because there will also be a lot of nutrients in the water fraction. And what can we do with that?
The first step is this dewatering step. This is a screen deck. You see, so the water falls through.
So it's just starting.
Yeah, and then the solid component kind of slides down to the next separator step.
Okay.
A screw here that transports the solids that fall down in this.
Pushes them upwards.
Pushes it
like
up.
An Archimedes screw.
Exactly.
Yeah.
So the idea is that the food waste gets pressed up here, pressure is built, and you kind of, like if you dry a towel, you know,
it's like that
press
wringing,
it out,
wringing
same
it
happens
out.
here,
Yeah.
and then it falls down in this container.
Amsterdam has a schedule of 75,000 apartments until 2050, new to be built. That will be mostly high-rise buildings, and they all can be connected to such a system.
But there is another type of waste that can be more challenging to deal with, especially when it gets into our waterways.
I'm standing here on one of Amsterdam's canals. This is actually one of 7 points in the city where water flows out towards the sea. And just in front of me here is the city centre and the central railway station as well. And of course, there's an awful lot of rubbish flowing out in the water from the city centre. And this is where it's collected.
What we've seen and what the science tells us is that cities are one of the major sources worldwide of the ocean plastics that we are also worried about. So what we try to do with the municipality is make sure that we catch it before it enters the river here and then enters the sea.
There's all sorts of nonsense in here. There's cups, fast food containers, glass bottles, plastic bottles. There's even some things that I won't mention related to the city's red light district. But all of it's being collected here, and I've come to find out how this device works.
What you see over here is a combination of a curtain, so a floating line, in combination with a catching system. And the curtain drives the plastic towards the system. The whole curtain makes it impossible for the trash to go out of the city. So the curtain needs to be deep enough in the water. So in this case, it's 50 centimeters. And also what you see is it's 20 centimeters on top of the surface of the water. So it's that the trash is not going over the curtain. And that's all based on water current and wind.
So the idea is that the rubbish kind of flows down the curtain and ends up. Is this what we're standing on? Is the
where we're standing on is the catcher?
Could we have a little look at what the catch is?
The system was emptied yesterday.
So this is just a day's worth of plastic.
Yeah, you see
even a light bulb in there.
Bottles, fast food, fast drinks.
What is that?
I think that one is for a flag.
For a flag, like a flagpole. It looks like. Yeah, you could be right.
The plastic that we catch in the catching systems, the most important thing that we do with it directly is tag it, categorize it, number it, create data points out of it. And we use that data to design preventive policies and to target the items that cause the most nuisance to solve the problem.
Is it the case now that for Amsterdam as a whole, you're trying to trap like all of the plastic exiting?
So you need to take a look at the bottlenecks.
The places where you can make the biggest impact.
The biggest impact. And the money that you put into removal could also be put in prevention.
Yeah.
Then you prevent those plastics, because this bottle is one bottle, but if it's broken down, at the end it is 1,000 or 1,000,000 microplastics.
Yes.
And try to remove those plastics in a cost-effective way. That's impossible. This gives insight in type of plastic, how much, and you stop the journey.
That's great. Thank you.
We like to view Amsterdam as a living lab where we try all kind of new things that haven't been tried before. We show how it works, we write the lessons down, and then other cities can replicate it. We hope it will also help to establish a different culture, a different consumption culture, in which we care about our materials and our resources and our landscapes and environments much more, and work together to nourish and maintain our own environment.
What I've been really struck by today was just that sense that you won't make a city circular by just a top-down diktat. It's got to be communities and researchers and policymakers kind of all working together. And also just how difficult it is, like all the work that's gone on so far. Important as it is, it's still really just a small part of the jigsaw. So yeah, it's still a long way to go.